Okay, this lecture is about binomial experiments and using them to simplify the hypergeometric, which as you may have noticed is a rather daunting formula. And so start out with a motivational example, which I think kind of covers the spirit of what a binomial experiment is. And factory, you have a machine that produces 12-ounce bottles. Okay, there is a probability of P equal to 0.02 that any bottle this machine produces will be defective. In a case of 24 bottles, what is the probability that 2 of these bottles will be defective? So what is a binomial experiment? Well, a binomial experiment has a fixed number of trials, okay, like hypergeometric. Each trial is either a success or a failure. Each trial has a fixed probability P of success. Okay, so here this is a difference. Has a fixed probability P of failure. With hypergeometric, you know, from one to the other, because it's sampling without replacement, these probabilities aren't fixed. The trials, okay, are independent of each other. The trials in a hypergeometric are not. There's a random variable, counts the number of successes. That's the same. We have a neat notation to denote binomial. It's X is a binomial experiment with n trials and a probability P of success. Okay. So we have this formula here. I'll show you the formula. The probability that X is equal to little x is n choose X times P to the X power times 1 minus P to the n minus X power. This first is the possible number of ways that X successes can be chosen from n trials. We take this times the probability of X successes, so P to the X is the probability of having X successes, and we multiply this times the probability of having n minus X failures. So the probability of failure is 1 minus P. If we have n minus X of them, okay, this is that probability. And so this is a formula that makes sense, and you break it down into 3 parts and memorize each of the 3 parts and then memorize it together. This is a way to approach it, right? This first right here, it's just n choose X, the standard combination coefficient. Okay. All right, so let's look at our problem again. A machine in a bottle factory makes 12-ounce bottles. That 12 is just a distractor. It's not coming in. There's a probability of P equal to 0.02. Any bottle will be defective. So here in this experiment, a bottle being defective is a successful. In a case of 24 bottles, okay, we're taking a sample size of 24. What is the probability that 2 of these bottles will be defective? What's the probability that 2 of them will be defective? So in this, the 24 goes to the top, the 2 goes down here to the bottom. This 2 is the same as this 2. This 0.02 is the P value here. This 0.98 is 1 minus P, and the 22 is 24 minus 2. So notice this number and this number will always add up to this number. This number and this number will always add up to 1. Okay, so 24 choose 2 is 276. 0.02 to the second power is 0.0004. 0.98 to the 22nd power is 0.64 to the 12th. 0.6412. Do the multiplication, and this comes out to 0.071. Okay. Now, here, we had mentioned that this connects with hypergeometric. How does it do that? Well, in a bowl that contains 150 peanuts, 50 of these have been tainted with salmonella bacteria. Ooh, bad stuff. What's the probability that in a handful of 15 peanuts that 3 will contain 3 that's contaminated? So this is hypergeometric. Okay, getting, in this way the language is set up here, getting a contaminated peanut is a success. Okay, so there are 50 contaminated peanuts. There are 100 that are not contaminated. We take a handful of 15. What's the probability of getting 3? And again, we feed the formula. This is something we've done numerous times in previous slides. This is 3, this is 3, this is the 15, this is 15 minus 3. You crunch the numbers and you get 0.127. Now, this calculating with these numbers here was, in the old days in particular, a pretty hefty job. It was they did not have calculators. They had tables of logarithms, and they just worked themselves silly. This would take a considerable amount of time to have done in the age before calculators. So, being smart folks that they were, they figured out an easier way to do it, or at least a less computational way, intensive way to get numbers that were close. What they do, and to use the binomial, you take the number of successes divided by the total number, and that's your approximation for p in the binomial. You use the same sample size, you use the same value of x, and you run through the numbers. Again, fill in the binomial in this way. And so what have we got here? The number is, okay, 0.13, so 13%. Previously it was 0.127. If you're going to round it off to the nearest percent, these answers are the same. If you're, if it bothers you to be off 12.7% and 13%, okay, this is going to be a problem. But quite frankly, most people don't grind the corn that fine. This is statistics, so this is a good answer. In fact, probably you're trading a half a day's work for probably about 5 minutes work, even before calculators. Okay, number 2, in a bin containing 1,000 bolts, 150 are defective. A sample contains 150 bolts. What is the probability that 15 of these will be defective? So again, the way the question is phrased, a success is a bolt being defective. Okay, so we have 150 defective bolts. Okay, 1,000 minus 150, there are 850 that are not defective. Take a sample of 45. What's the probability that 15 of these are defective? Again, you run the numbers, and here in the age of calculators, this isn't too bad. Okay, run it, and it works out to 0.0009. Okay, so 9 in 10,000. Almost 0. If you're interested in just percentage, this is like 0%. Okay. We do the binomial. Again, number of successes divided by total population. You get a p equal to 1 point, or to 0.150. Okay, we have a sample of 45. Okay, goes right there. What's the probability 15 of these are defective? Okay. And you run the math on it. You run out your binomial. And here it turns out to be 0.0010. So we're off by 2 10,000ths. And again, if you're rounding this off to the nearest percent, it's 0. Okay. Example 3, in a shipment of toilet paper, and I said shipment, 14% of the rolls have been mistakenly treated with itch powder. In a package of 12 rolls, what is the probability of that 2 of these rolls will suffer from this mistake? Okay, again, this is a pure binomial one that has a certain proportion of them being successes. Getting the itch powder apparently is a success. That's the way the question is phrased. N equal 12 for the sample size. What's the probability of getting 2 of them? Okay, then we run the math. Okay, and there's not a way to work this hypergeometrically, but who would want to?